So welcome today. It is our pleasure to listen to Chris Judge's second lecture of this gemstone mini course on variations of geometry and spectrum. So today's lecture will be on analyticity. And if you at some point feel you missed something from last time or you want to remember, we just wanted to let you know that the lecture from Friday is available on the website. So you'll be able to catch it. But without further ado, please share your questions to the speaker through the chat or by unmuting yourself. And Chris George, the floor is yours.
Yeah, thank you so much, Laura. Thanks everyone for coming. So this is the second lecture. And last time I talked about continuity of eigenvalues, eigenfunctions, and really trying to emphasize eigenfunctions. And today I'll talk about analyticity. And so these are the topics I hope to cover. We'll see how far I get. So first I want to state a basic result, originally due to Relic, again, about analyticity in the case you have symmetric operators, in particular finite dimensional, but as I tried to intimate last time, if you have compact resolvent, then you can reduce to the finite dimensional case by doing a projection. So, and then I want to immediately go to applications before taking up the proof. And there's two applications I have in mind that are close to my heart. And one is generic simplicity for eigenvalues, and the other is concerns the existence of what are called Moss-Kuss forms, which are objects in the theory of automorphic forms or modular forms. And then I want to talk about the proof. In fact, Relic's original proof, which I like very much. I didn't actually read his proof until very recently. And I like the proof. And then if I have time, then I'll talk about two-parameter families. So everything today is about one-parameter families, and in fact, two-parameter families and multi-parameter families are very difficult to deal with for various reasons. Okay, but before I get into that, my former student Neil Coleman pointed out after my lecture that I should have probably said something about normalization of eigenspaces, normalization of the domains of these quadratic forms that I was dealing with. So remember, the F, we have, I have this, I was thinking of the Rayleigh quotient, calling it Fn for some family of domains, omega n, some omega n family of domains, and I'm assuming sort of that omega n is converging to omega, and so in particular the domains of these Rayleigh quotients, it's not normalized. It's changing as n changes. So I should point out that, I mean, there are different ways of doing this normalization of the H1, but it involves some choices, and there are many different ways, and oftentimes part of the problem is actually to do it nicely. One simple example of doing this is simply if you have a family of maps which take your original domain omega onto omega n, and you have some regularity of these maps, and then you just look at the pullback. So H1, all the H1 functions pull back, that is, you precompose by this diffeomorphism or this map, which for large K is going to be a diffeomorphism, because I'm assuming it converges to the identity map. And you can pull back H1 functions to H1 of omega by this map, if it's suitably regular. And then what you consider, instead of considering these Fn's, these functionals on H1 of omega, and you should consider the composition. And so, but it's still that composition is still a ratio of quadratic forms. And so all the analysis we discussed last time still applies. It's just that you get variable coefficients in your Dirichlet form, etc. Okay, so that's something. I shouldn't minimize this. This is a part of the game that you have to play, but it's something I'm not emphasizing.
Chris, can I ask?
Sure.
Hi, Chris. So this is done.
Hi.
So can I ask what does this method work also if the topology changes, like you add a tube, for example? And
No. So in fact, yeah, good points. Yeah, for last time when I had this topology changing, then we certainly don't have diffeomorphisms that work like this. So you really have to work on an ad hoc basis. So you have to find some sort of inclusion of H1 of omega inside H1 of omega n, or vice versa, and you have to be careful about this. So this is a very limited example of the kind of thing you have to do. In general, it's something you have to do ad hoc. Yeah, thank you.
Because it was not clear to me when you add the tube and you take epsilon to 0, you don't get finally a separate a disconnected space. You get a space connected by a line, or right? It's not clear.
But in this and so in some say, so if you look at the Dirichlet problem in that case, you have to be very careful, because then, and also if you look at the higher modes, you have to be careful. I was looking at the lowest mode, so in some sense that's cheating. And the lowest modes, I don't really have it's easier to deal with. But in the higher, when you look at the higher modes, there could be spectrum coming from the actual limiting tube. There's a line segment.
Yes.
So there's work of in that direction. There's work of Jimbo and Morita, and also Ariata. So it's actually, there's a lot of work that goes into that. I was trying to make it much simpler than it actually is. Yeah. So there's lots. So I would suggest looking at the papers of Arieta, for example. Yeah. Right. Yeah. And we could have a course on that kind of stuff in particular. There's also work of Gattelchen. Okay. And also recall from last time, F was a quadratic form, or was a ratio of quadratic forms. It's a Rayleigh quotient. And I was talking about these spaces EM, which are in some sense they're just the critical points, or the span of the critical points where the critical values are less than M, or in other words, they're the eigenspaces up to some value M. And the proposition that I was proving last time was this one, that as long as M is not a critical value itself, or it's not an eigenvalue of your operator, then the eigenspaces converge. But I have to say, I wasn't very careful about what did I mean by converge. So let me be more specific. What I meant was Hausdorff convergence. So these sets are converging as sets. Okay, and there's two parts by Hausdorff convergence. I mean, a set converges to another set if given any sequence in AN inside capital AN. If it converges to some B in your space, then B has to be an A. Okay, so that's one thing. And in some sense, the critical points do satisfy this in general. And so this is not really the issue. In general, the issue is more about stability. If you start with a critical point in your limit, can you find some subsequence which or sequence in AN which converges to that? and that's more about stability. And the example I was giving last time about that was simply this example of a cubic. If you have a cubic, and then at some point, the critical point set is empty. You have a family of cubics. So that was the example from last time. So that example was to get rid of stability. So I had this, so at time equals, at negative time, I look like this, and then at time equals 0, I get like this, and then for positive time, it has no critical points. But that means that, so if this is ft of x is equal to, say, t cubed minus, or plus xt, I guess, yeah, plus xt, x cubed plus xt, then you should look at f1 over n. So this sequence won't be stable. The critical points won't converge because for positive t, the critical set is empty, but at t equals 0, or when n goes to infinity, the critical point set is not empty. So you don't get Hausdorff convergence. Okay, so that's something I wanted to clarify. Does that make sense? Yeah. Good. Okay. Okay. And then last time I also mentioned this example of relic, and that's part of the reason that we want to talk about analyticity. So in particular, if for example, if you can find a smooth family of matrices, so there's a smooth family of matrices. I didn't do this calculation, but you can check that this is the conjugation gives you this. The family of matrices has these eigenvectors depending on t, but they don't vary smoothly at all at t equals 0. These eigenvectors, they're just, in fact, not even continuous as t goes to 0. But the eigenvalues are. The eigenvalues here are for r. So that we have a smooth family of matrices for which the eigenvalues are smooth, but the eigenfunctions or eigenvectors don't even converge at t equals 0. So that's an example from last time. But later on, I don't know that this is the first time it appeared, but this is the first time I have a reference for it, is Relic proved that in general, eigenvalues are continuous. In fact, if you start with something that's C1, some n by n symmetric matrices, a family of them, and this family is C1 and T, then the eigenvalues are also C1 and T. Okay, but the thing is, this example up here tells you the eigenvectors need not be. So eigenvalues can be very nice, and they are for nice if the family is nice. But the problem is with the eigenvectors. And again, what I was trying to emphasize last time is that the problem arises when you end up with some multiple eigenvalue. Away from the multiple eigenvalues, everything is good. But when, like here, the eigenvalue you get is 0 in the limit. As t goes to 0, these two functions go to 0. And so I have a multiple eigenvalue of 0. Okay. And the other thing, yeah, so again, I want to point out that I've been focusing on finite dimensional situation, but again, if you have a Laplacian, it depends nicely on t, for example, then you can project onto a finite dimensional part as long as m is chosen to avoid the eigenvalues, and so you can you can apply the projection that gives you to apply, and that gets you to a finite dimensional space, and then you have Laplacian, then you apply. Now, of course, this projection depends depends on t, and you need to look at these vector spaces will actually be moving. If it's analytic or even continuous, you can adjust these vector spaces to look nice. So this is there's a There's a step which I'm not emphasizing, which is to go from some infinite dimensional situation to a finite dimensional one, but with some work, you can do that. Okay. Okay, now I want to go into analyticity. So, and one of the main reasons is because the eigenfunctions don't seem to behave very nicely, even when you talk about smooth families of matrices or smooth families of operators. So, but analyticity, if you're in the self-adjoint situation, then things work out rather nicely. So that's what I want to explain today, or at least today. Okay, so the setup is, let's take V to be a complex vector space. Let's assume it's finite dimensional. And now it's going to be a complex vector space. And I'm going to look at a Hermitian inner product. So we put the conjugate sign on the second variable. And I'm going to look at a family of operators from symmetric matrices, if you like, or matrices, if you like, from my finite dimensional vector space V to V. And I'm going to assume that the family, and here T is going to be a complex number. So sometimes I want to restrict T to a real number because in applications, but for the proofs, we're talking about T is in C. And we're assuming that the family T goes to AT is holomorphic on some open set. So here's my open set U in the complex plane. I'm assuming that this, of course, you know, what this means, if these are matrices, if you like, is that all the entries depend holomorphically on T. And in general, what you can do is you can use the inner product to define projections, and you want each one of those projections to be holomorphic. Okay, and then the theorem of Relic, it's from his first paper again that I mentioned last time, is that if you, oops, yeah, there's a little typo here. If you know that for T in the complex numbers or inside the set U, that the adjoint, the Hermitian adjoint, is equal to AT bar, where this is bar means complex conjugate for all T in your set, then you can find a slightly smaller set in green here, this set here, that meets U prime on the real numbers. They agree on the real numbers, and so that you can find holomorphic lambdas and that are, oops, this should be, oops, and holomorphic U's. So those are my eigenfunctions. So these are eigenfunctions, right? So they're eigenfunctions. And moreover, for each individual T in this U prime, V can be written as the sum of UITs. And it's orthogonal if T is in, this is an orthogonal direct sum if T is in R. Of course, because symmetric matrices, when, I should point out, when this condition up here, this is just saying when T is in R, this is just saying that A is symmetric. Okay. And of course, eigenvectors are orthogonal from different eigenspaces are orthogonal if you're in the symmetric case. So that's the basic statement. Okay, any questions about that? Well, the chat's very silent today. Okay. Okay, so that's the basic theorem. So let me jump in.
There's a question by Alexander in the chat, asking if Relic stated this for bounded operators in infinite dimension.
Right. So, so in the the part of the paper I'm looking at, he stated for finite dimensional stuff. I have not read the whole paper. I actually I only about 2 weeks ago. I found the paper and I got Claude to translate it for me, and then but this is actually theorem number 1 in the paper. Later on, I imagine there may be some discussion about what happens in infinite dimensional stuff. But I think even then they understood that that understanding what happens in finite dimensions is really enough given compact resolvent. And if you look at Kato's book, for example, the first half of the book is about finite dimensional perturbation theory. And then later on, after giving a course in functional analysis, Kato says, okay, now everything applies if you have a compact resolvent. Okay, so yeah, thank you, Alexander. Yeah, okay, and so now, so why is analyticity such a wonderful thing? I mean, well, one good thing about this theorem is it actually tells us that the eigenfunctions will vary continuously in the parameter t. We didn't even know that in the smooth case. Okay, that's a given. But analyticity gives you sort of global implications because of this wonderful fact that if you have an analytic function or a holomorphic function and you take it the inverse image of 0, its zeros, they form a discrete set unless, I guess I need to say, unless f is a constant. If you have an accumulation, well, 0. So unless it's identically 0, then your zeros are discrete. Basic complex analysis fact. But that's wonderful because now it tells you that unless your function is a constant, or in particular 0, then there will be a lot of places where it's not 0, and not 0 may be a good thing for you. Okay, and that's what happens in these examples. So in the first example, it's an example for simplicity of eigenvalues. Yeah, suppose we're just in the real line, and analytic means here convergent power series or the restriction of the holomorphic function defined near the real line. And suppose you know that for some t naught, the spectrum is simple, then this will imply that the spectrum is simple for all but a countable set of t. And it's a simple idea. The proof is very elementary. We're going to apply this basic fact to the difference between two eigenvalues. So I may have these. I know that the theorem of Relic tells me that all these eigenvalues vary analytically. Notice, by the way, these are not ordered eigenvalue branches because when they cross, their ordering changes. So, but I have these analytic functions, and I can label them however you want. That's not an important labeling. And where they cross is exactly where some analytic function is 0. So I know that set of crossings is discrete. And so if I fix a level m and I look at all the crossings under level m, that gives me a nice discrete set. And then I can raise m and I can take a union of countable sets and it's still countable. So I'll get simplicity. Of course, I needed to know that each one of these, that there was some, well, there are different ways of doing this hypothesis, but one hypothesis is that I know there is some t naught, so that each one of these is actually corresponds to a simple eigenvalue. That is one-dimensional eigenspace. And then I can run with that. Okay, any questions about that example? That's the simple example. I can't, this wouldn't, of course, work if I just were talking about smooth eigenvalue branches. This would, yeah. Okay. And then the other example is a little bit more intense, which is about Moss cusforms. So here, X is a hyperbolic surface with cusps. And the typical example of this is take the hyperbolic plane and mod out by SL2Z, which is what I pictured on the right here. The gray region is the usual fundamental domain for H2 mod SL2Z, but of course this is a much more interesting, or no, there's no more interesting example. This is the interesting example, but there are other examples. But you know, there's a question as to what the eigenfunction, what the spectrum of this thing looks like. And Selberg studied this a long time ago, and one major result is that, in fact, even though you have a continuous spectrum, due to the fact that you have this infinite cusp going out to infinity, you have this cusp going out to infinity, there's actually a continuous spectrum starting at a quarter. There can be actually embedded eigenvalues. And Selberg, amazing proof is showed that, in fact, there are infinitely many embedded eigenvalues. In fact, they account for Weil's law. And so then the question happened, that's for SL2Z. But then the question, well, what about for other congruents, or no, sorry, other quotients, not necessarily congruents, quotients. What happens for other hyperbolic surfaces? And there's a whole moduli space of such things. And then many people have worked on that question ever since, and it's still unresolved as to what happens for, say, the generic hyperbolic surface with a cusp. It's not known whether you have infinitely many, although there are, I mean, okay. I'm assuming that we have a complete hyperbolic surface, finite volume, non-compact. Okay, in for this particular situation in hyperbolic geometry, the Rayleigh quotient looks like this, actually. After you work out what the appropriate gradient is and what the volume form is, this is going to be your, so here I take the ux means the x derivative of u and the y derivative of u, and x is this way and y is this way as usual. Okay, but then Lax and Phillips realized that they could understand this this situation by restricting this Rayleigh quotient to the set of functions for which, well, what I should say is that it's understood what's responsible for the continuous spectrum. It's the zeroth Fourier coefficient. If you think about the zeroth Fourier coefficient as the integral of the function going across this way, then that's responsible for the continuous. So Lax and Phillips said, okay, so let's restrict to those functions u, so that the zeroth Fourier coefficient is 0. And let's, of course, we need to start that somewhere, and we start that at y0. So I'm going to look at integrals of the function here. And I assume that for all y bigger than this y0, that's always 0. And what they showed is that if I do that, then the operator that I get, of course, I have a Rayleigh quotient, and last time we saw, given a Rayleigh quotient, we can end up with an operator, and the operator in this context called the cutoff Laplacian, and it has compact resolvent, which means that now I talk about discrete spectrum. I have finite dimensional eigenspaces. I can run perturbation theory, for example. Everything is good. So this is in Lax and Phillips' book from 1977. From the automorphic forms perspective, it turns out that you can check that U is a Moss cusp form. What does that mean? It means actually the zeroth Fourier coefficient is 0 all along for every Hoare cycle. Okay, and because eigenfunctions are analytic, and they satisfy the zeroth Fourier coefficient satisfies an ODE actually. to check whether the fact that I have an eigenfunction, which is for this operator, the cutoff Laplacian, whose zeroth Floyd coefficient is 0 above y0, to know that that's actually a eigenfunction, true eigenfunction of Laplacian. All I need to know is that whether this is 0, this derivative at y0. If it's 0, I'm good. Then I know it actually extends. By ODE theory, I know the zero Fourier coefficient has to be 0 in the entire thing. Okay, right. So having a critical point or eigenfunction for the Lax-Phillips cutoff Laplacian and this condition, if and only if U is what's called a Moss-Kuss one. So now let's suppose we have a family of hyperbolic surfaces, and it's analytic in however you want to think about analyticity, and there are many people who think just about this kind of question for hyperbolic surfaces, or it did. Then the Rayleigh quotient you can show as analytic. If you pull back the appropriate functions, blah, 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 just in the same way I discussed at the beginning. And so what that tells you is that just like with the simplicity case, if you know there exists some T naught so that X T naught has no Moss-Kuss forms, then this implies that xt has no Moss forms for T in all but a countable set. So here I'm assuming again that T is in some interval. And so just knowing the existence of one that doesn't have any Moss-Kuss forms means that basically almost all of them in that family don't have. Okay? And so that was a remark made in a paper of Phillips and Sarnak in 1985, but they credit Lax with this. Uh-oh, I just saw Zeb pop up. Sorry, Zeb, what did I do wrong? Hey.
No. I'm just trying to remember this stuff, which is antediluvian, but right now there is no single T naught for where this is known, right? That's the state of the art. Okay.
Yes,
good.
thank you. The state of the art is we have no idea. This is open. This is open, yeah. Yeah, thank you. Thank you for the question. Yeah, we don't know. It's an amazing thing. And people have been working on it, well, I don't know how many people have been working on it, but people have thought about it since, early 80s. Yeah. Okay, so that's the other application. Notice that this application is a little bit different than the other one because this one has to do with the U's, not the lambdas, right? So here we're using the fact that the U's are analytic to understand this condition. This condition, this depends analytically on T because the U's depend analytically on T. And we want to check whether this condition holds or not. And what this is saying is that if you have some place where that condition doesn't hold, right? It doesn't hold for all the different U's, then it doesn't hold for almost every T. Okay, any questions about this example? Okay, so now I want to try to give the proof of Relic's theorem. So that was the application part.
Alexander is asking in the chat what the conjecture is.
Oh, the conjecture is that there are no Moss-Kuss forms for the generic gamma. So there are different variations of the conjecture, but there are even stricter ones, like it doesn't have, I think Zeb told me, globally adelic Eisenstein series or something. I mean, but I think the easiest thing to state is that for the generic gamma, for the generic gamma, that's a cofinite subgroup of SL2R, there are no Moss, or there may be only finely many Moss cusp forms. You can always have small eigenvalues, for example, but there's finely many, say. Is that good? Okay.
I think that's the state of the art. You probably have to exclude the symmetry if there's like a reflection, like if SL2Z, then the odd ones are automatically cusped. But so once you formulate it sufficiently carefully, then that's the conjecture, and I believe nothing is known about it.
Right, yeah. So, I mean, in some special situations, you can have fine cusp forms that you don't expect, but with symmetries. But if you take just a random surface, I don't expect any, or at most finely many. And that's completely open. We don't know a single example of something which satisfies this. But we believe that it's generically true. Okay, so yeah, maybe I should give a name to it. It's called the Phillips-Sarnak conjecture, or Phillips-Sarnak philosophy, some people have called it. Okay, so now the proof of Relic's theorem. So yeah, I really like this proof by Relic. This is, again, in his original 1937 paper. Let's assume we have a finite dimensional vector space. We're talking about a holomorphic family of functions, just as before. And of course, when you're talking about a finite dimensional operator, we're talking about the roots of the characteristic polynomial. So we have, here's my characteristic polynomial, and I'm looking for its roots. And that's a Weierstrass polynomial. It looks like it has this, where now the C's are coefficients which are holomorphic in T. And the set where I vanish forms a curve or a Riemann surface. And it's, in fact, gives you the map from T comma Z to T is a branch covering. So I have this Riemann surface, and it's sitting over the variable T. And for every T, the eigenvalues are essentially the fiber of this finite branch covering. Right? The fiber is finite. And the branch points correspond to the multiplicities. And so I have this branch covering, and I can talk about local sections of this branch covering. So I can move, I can take some and do, I lift, right? I may have problems lifting through the loop through the branch point, but nonetheless, I can try to talk about local sections of this fiber bundle. And the issue, one of the difficulties, and it's that probably is not clear at the beginning, is that in general the monodromy of this is non-trivial, of this fiber bundle. So this is also, I think this example is also due to Relic, I believe is. Let's just take this family of matrices 0, 1, T0. Okay, so then you can see the characteristic polynomial is e squared minus t, and we get so it's the Riemann surface is a double covering of the t equal t plane branched at 0, and we get sort of the eigenvalues are plus minus square root of t, right? But this is very bad, right? So this is well, it's bad from a spectral point of view because this is not an analytic function. Or if I restrict, for example, to the real part of t, then this is the square root. Square root is not very nice. So in general, in fact, you won't have analyticity but this is not a symmetric matrix, so it's not the situation that Relic was talking about. Okay. So Relic has a couple of lemmas, which I've summarized into this particular lemma. So because he's looking at he has this condition that A star t is equal to A t bar, he's looking at a very special kind of family of matrices. So this is at t, when t is real, this is just the symmetry condition. And it's because you have this special condition, your characteristic polynomials are also special. And in particular, the characteristic polynomials satisfy these two conditions, this condition and that condition. Okay, so, and then the lemma says that you basically, if you have these two conditions for your Weierstrass polynomial, or characteristic polynomial in this case, then you get trivial monodromy. So you can actually, you have this sheet, this covering, normally a covering that winds around your branch point, but what happens here is that, and it may wind several times, but here something winds around just once, and so when you look at this thing, it looks like a diabolo or something. It's just a bunch of planes, which complex planes which have been glued at the point. Okay. And each of those complex planes corresponds to an eigenfunction or eigenvalue. And then each of those corresponds to an eigenfunction. So because of this condition, it turns out that everything is nice. Otherwise, what you have is something called a Puiseux series. Pardon my French. Puiseux series. Okay, and that's a more complicated situation, but people do deal with it in the case of not having symmetric matrices. It's just not as nice. You have things like this that go on. Okay, so maybe I won't go through the proof, but Jean has assured me they're going to post the notes, and I really like this proof a lot. That of this lemma, you basically have to try to understand you want to show that you have trivial monodromy, and so you consider you lift a path from the t-plane into your surface, into your Riemann surface, and then you have to check that. Oops, you have to check that that when you do this, that everything winds up ending up at the same point. That you don't end up going around maybe several times before you come back. Okay, and you use conjugation. Here's where you use the second hypothesis. Here's where you use the first. It's a very nice proof. In the end, once you get trivial monodromy, then you use the fact that you can remove singularities if you have a map between a Riemann surface, two Riemann surfaces. You can remove that's holomorphic, mapping a punctured something to a punctured something. Then you can Riemann's removability, Riemann's theorem on removable singularities can be used to actually get to extend your sections, your global sections, to 0. Okay, and then each of these sections are on your curve, and that tells you that you can write this Weierstrass polynomial, which is a monic polynomial, as a product of z minus the roots. Okay, so I'm running. I don't think I had time to really give the go through step by step, because I want to get to this other part, which is more fun. And then you have to check that those conditions are, in the case of Relic's theorem, where we have a matrix A, you want to check that those conditions are true, and here's where I check them. Once you have the lambda i's, then it's not too hard to generate the ui's. There is one technical detail, is that it could be that you could have a sheet of this covering which corresponds to a multiple eigenspace. So you could have one of the, so you have these, the monodromy is trivial, you get these sheets, and then you could have a two-dimensional eigenspace for one of those sheets, in which case you choose an orthonormal basis, and it's not hard to show that that orthonormal basis actually varies nicely as you move along that sheet. The key here is actually to separate the sheets. Okay, yeah, so that was a very sketchy sketch. Any questions about what I might have said? Okay, good. Okay, so let's go to the very end. Oh yeah, by the way, this theorem, Kato, Kato's not one for being very flamboyant in his writing, but he made this remark that the existence of this theorem, basically, he's saying this theorem is basically, you know, one of the most remarkable results. It's remarkable. It's a kind of an amazing fact, which is maybe not so appreciated unless you actually go into the proof.
So there's a question in the chat by Alexandre asking if the proof is explained anywhere more recent than the original paper in English or French.
Right, good question. Yeah, so I don't know. I mean, maybe, but I can send you my Claude's translation if you like. We could post it of the original paper if you're worried about French or English. Yeah, but the Kato's proof is different, and I have to admit, I can see that Kato is trying to understand monodromy, but I really don't get his proof. Maybe someone can explain it to me, but it's clear he's trying to do monodromy. But anyway, this part I think is much clearer for me in Relic. So everything that I've in Relic's papers, I think, is in Kato. I think he's basically, it subsumes Kato's book subsumes Relic, but there are differences in how they prove things. And in this particular case, I like Relic better, or at least I understand Relic. Okay, so now I want to, the last topic of today, two-parameter families. So this is, you know, we're talking about analytic family in one direction, T, and then now what if we have in two parameters? Well, things go awfully wrong, and they go so awfully wrong for some reason. I think the development of this, in some ways, the subject sort of has stopped. I don't know a lot of work on the two-parameter situation. There should be more work because it's a very interesting situation. There is a paper of Lenny Friedlander that discusses this kind of stuff that people should look at, but there's not a lot of work on these two-parameter things. And one of the reasons is things just go awfully wrong. So in particular, here we have a nice symmetric matrix. This is a nice symmetric matrix. And if I compute its characteristic polynomial and then I its roots, I get something that looks pretty bad. So this is non-analytic function. This is the graph of this thing. It's a multi-valued function, obviously, and the graph of it is a cone. If I look in the real coordinates. And you know, you might be wondering, well, where does the proof fail for this? Well, you know, it's, you know, working with Riemann surfaces in some ways is easier, and in particular, you have the removable singularities theorem. You have this one singularity, and we understand the monodromy, and then we can remove it. The function extends holomorphically. That doesn't happen in the, you know, well, there's Hartog's theorem, but it's not enough to do something here. By the way, this this might be called Dirac cone because this kind of situation shows up in topological insulators. All this physics that's been going on for the last 50 years. You'll see this kind of picture. It's just the parameters are no longer, the parameters will involve dispersion momenta or something. And anyway, I don't know much about that, but this is an example which shows you that more parameters is bad. But this picture is actually kind of nice. It does have some interesting features, and it is something that you have to deal with. I mean, sometimes you do have a multi-parameter system and you want to understand what's going on. And one nice feature of this is that it gives an explanation for something called crossing avoidance, which is an interesting topic. So back in the early days of quantum mechanics, when they were actually plotting what some energy levels might look like if they change the parameters in their system, apparently they started seeing early on, they started seeing situations where they had one eigenvalue doing this and one eigenvalue doing that. But these eigenvalues apparently wanted to avoid each other. And it's called crossing avoidance. And so it's just kind of a mystery. Why don't these eigenvalues want to cross when I change my parameter t? And what they realized is, in fact, that what we think of, the thing that explains this heuristically is the following, is that if you now take your parameter t and you include another parameter, then it's very likely, in fact, that you're going to see you'll see a cone. These cones are not just exist, but in some sense, they're sort of the simplest singularity you can expect to exist. And for 2 dimensions. So if you take so now, if I choose a particular plane, I fix T2 to be equal to some constant. And then I vary in T1, then I'm taking a conic section. And when I take a conic section with a plane, a vertical plane, I'm going to see this picture. Okay, so this is sort of explains why this is happening. So and in fact, this sort of was understood by Wigner and von Neumann in the 1929 paper. Another one that you can now translate using your favorite AI. And the idea is that matrices with multiple eigenvalues are codimension 2 in the symmetric matrices, m by m symmetric matrices. So if I take m by n symmetric matrices and I look at the matrices which have multiple eigenvalues, that's a codimension 2 set. And so it means that that's why I usually see when I look in a plane, I look in a particular plane in my set of symmetric matrices, and I look at the eigenvalues, I'm not going to usually see. So here's my plane of take a plane inside my set of symmetric matrices. I'm not going to see multiple eigenvalues occurring in a curve. I'm going to see them in a codimension 2 way, which is a point. So I'm only going to see one point in my plane where I have this multiplicity 2 thing. So that was the explanation. And the proof is fun exercise. It's basically one way to think of it. This is not the only way to think of it, but O of n acts on the symmetric matrices by conjugation, and there's different isotropy depending on which point you're talking about. So the isotropy is discrete if the matrix has no multiplicities. So in particular, what this does, what I mean by discrete, is you can have permutations of the eigenvalues themselves. You can list the eigenvalues lambda 1, lambda 2, lambda n, and you can permute those bases. And so up to some permutations, the action of O of n is free. This by conjugation. But if you have multiplicities, then you will have some continuous isotropy, meaning you have an O of, say, an O of k, where k is the multiplicity, because you can in that eigenspace, you have O of k acting. So so the dimension of those of the situations where you have no isotropy, sorry, where you have no multiplicity, well, you have to specify these n eigenvalues, and then you have to conjugate. And the action of conjugation, it's free on those, and so you just have to add the dimension of O of n. And that ends up, if you calculate out, you get what you usually get for the dimension of the symmetric matrices. But if you have some multiplicities, then you're going to have to mod out by a stabilizer. Mod out, I mean, here you had to mod out by a stabilizer too, but it was discrete, so it didn't change the dimension. But here I'm modding out by the stabilizer, which is continuous, an O of 2, or maybe an O of k, let's just say an O of 2. And I also only have n-1 eigenvalues to prescribe, because the last two, for example, are the same. So there's only n-1 eigenvalues to prescribe. And then there's fewer dimensions because of the isotropy, and so I end up with codimension 2. Okay, so that's a cool fact. I really love this fact. In fact, but I'm not the only one who loves this fact. If you know this book, this is Peter Lax's linear algebra book, wonderful book. And in fact, this whole thing is described. He gives a much more concrete and probably better for students proof of what I just gave in this book. And on his in the front of the book, these are the crossing avoidance. These are one of the exercises Lax says is in his book is take a computer, run MATLAB, take a family of matrices, generic family of matrices, and run MATLAB and compute and graph these eigenvalues and see miraculously this crossing avoidance. And so that's one of his exercises. Okay, so maybe I stop there. Thanks.
Sorry, thank you very much, Chris, for the great lecture. We have time for a few questions, I believe. Please feel free to unmute yourself or ask questions in the chat.
May I ask something?
Of course. Then.
Sure, of course.
So you mentioned this, you discussed this fact that there's, you can prove simplicity of the spectrum if you, or generically, if you have one guy that's simple, right? And then you have this other beautiful papers where you do it for Euclidean triangles and for hyperbolic triangles. Is there something that you can do for hyperbolic surfaces, not hyperbolic triangles?
Right. So my work with Luke, one of the things that it depends on the fact that to get that, we do want to get this in some sense. Where was the application? Yeah. No. Yeah. We want to fulfill this condition. And for some triangle. So we were considering hyperbolic triangles, for example, that looked like this. They're almost like that, but where the oops. Yeah, so we were looking at a triangle that that looked like this, where this is some angle alpha, say, and this is pi over 2. So this is in the upper half. And yeah, yeah, so we eventually, for that, we were able to do this, but it requires a lot of work that involves understanding what happens when alpha goes to pi over 2. That is, when the triangle gets smaller and smaller, we had to look at a situation where these triangles become infinitesimally thin. And once you do that, then sort of essentially the idea is heuristic is that then you can understand this through a one-dimensional problem or a sequence of one-dimensional problems involving ODEs. So you can talk about ODEs in the limit. You can sort of almost approximate, for infinitesimally thin triangles, you can understand the eigenfunctions through ODEs. But the issue is, for hyperbolic surfaces, there's no such deformation. If I take a complete hyperbolic surface, I can't create a one-dimensional problem by deforming. They're too rigid. A complete hyperbolic surface it resists, like the area is fixed, right? The area is equal to the Euler characteristic or something times pi. So whereas here I can make the area go to 0. And so that's the problem, is I don't know how to make,
because the area is dictated by the topology that's in the surface space.
and it's constant. It can't be
Degenerate.
Yeah, I can't make a degeneration like I can here. The way we did better than, say, Sarnak or Phillips and Sarnak and Wolpert is that here we did a very degenerate thing where we just killed the whole surface, and for regular hyperbolic surfaces it's not the same. Yeah, don't know how to kill the whole surface. Can't kill the whole surface. Yeah.
Okay, thanks.
You're welcome.
Thank you. Does anyone have any other questions? We have a few thank yous in the chat as well. In any case, I'm sure everyone will be very happy to keep asking the more questions tomorrow at the last session, which will happen at the same time and be on transversality, if I'm correctly informed. In any case, thank you so much again, Chris, and see you everyone tomorrow.